Hello, welcome you all. This is Dr. Sunil Mahagaonkar, Faculty of Mechanical Engineering Department, Government Polytechnic, Mumbai. So in the last session, we had discussed design of joints that includes knuckle joint and coil joint. So in this session, it is module number 15. I'm going to cover the design of keys. So this is one of the prime elements, as the name indicates, key. So without that we cannot operate anything. So like that. So we are studying what are the different applications and design aspects of key. So let us we will go with the slide. So what is a key? These are the learning outcomes. The types of keys: saddle keys, drift keys, cylindrical keys, sun keys, and the various application of all these types of keys we are going to study it. The materials used for the keys. So usually the shaft and the keys material are same. It is of mild steel or steel. So 45 C8 or 50 C8 is the material we are generally using it. So design of keys. So in that we are going to discuss the square sun key or flat sun key. So the main function of the key is to transmit the torque from the shaft to the mating parts. The mating parts of the hub, pulleys, above the pulleys, gears, flywheels, and other devices, so that we can transfer the torque to the other shaft. So the secondary function is to prevent the relative motion between the shaft and its mating parts. So this is very important, because if there is a slight clearance is there, or if there is a torque is, if the flywheel or the pulley is slipping over that shaft, it will not transfer 100% torque. So that's why, so we have to insert a keyway, key in the keyways provided in the shaft as well as the hub portion, so that we can achieve 100% of the torque. So anyhow, with the belts and all, we are not getting 100% of transformation of torque from one shaft to another shaft. So that is the different aspect. So keys are always inserted parallel to the axis of the shaft. So we are providing the keyways in the shaft as well as in the hub. The key is a different material, so that's why definitely we are going to get a contact stresses. That is a type of crushing failure you are going to get it. And since it transfers torque, so shearing stress. So it is designed based on crushing and shearing stress. Keyways is a slot or a recess in the shaft. So because of this keyways, the strength of the material becomes comparatively less than the solid shaft. So this is the one of the drawback of this. So the keyway is a result of stress concentration in the shaft, and the part becomes weak. Okay. Keys are made up of plain carbon steel, that is 45 C8 or 50 C8, in order to withstand shearing and compressive stresses. Okay. So generally the strength of the material for the key is more than yield strength of the material is should be more than 600 or 700. That is the tensile strength of this material. It should be more than 600. That is around 650. It is best for the key. Okay. So in the types of keys, we are going to learn some sun keys. In that types also we learn what are the types of sun keys. Saddle keys are the light keys, tangent keys, round keys, and the integrated shaft, that is splined shaft. The sun key, a sun key is one in which the thickness of the key fits into the keyway of the shaft and the remaining half of the keyway on top. Use it for heavy duty application. Okay, so this is the portion of the shaft. This is the half portion is there in the shaft, and half portion is there in the half portion of the mating part. And generally it is tapered on the top surface. So 1 in 100 it is given. So for easy removal of the key, where W is the width, which is equal to 1/4 of the diameter D of the shaft, and T is the thickness, which is equal to D upon 6. So the first one is the rectangular key. As I said, the width is equal to D upon 4 and thickness is D upon 6, and the taper is 1 in 100. Square key is one in which the width is equal to the thickness. The parallel sun key. The parallel sun key is one in which it is a taperless. So bottom as well as the top, the surface is a flat totally, and they are parallel to each other. So this type of key is used for shifting and the mating gear in having an axial movement along about its axis. So along the axis. So about the axis it will transfer the torque, but along the axis it will transfer the axial motion. So it is used where the pulleys and gears and other mating pieces are required to slide along the shaft. These are the parallel sun key. The zip head key, it is a rectangular sun key with the head at one end, and that is known as zip head. So it is provided for easy removal of the key. So this is the provision they have made, the zip head. Okay. So a taper sun key is uniform in width but tapered in height. So the top is plane is tapered. The standard taper is 1 in 100. The reasons for that is given below. When the key is inserted in the keyways of the shaft and the hub and pressed by means of a hammer, it becomes tight due to the wedge action. This ensures tightness of the joint in operating condition and prevent the loosening of the part. So the taper is also provided for the easy removal. This is the second advantage. So to have a dismantle the joint and for the maintenance purpose. So feather key. So a key which permits the relative axial movement. A relative axial movement. So this is fastened to the in the recess of the shaft by means of a set screw. And this mating part, it can have an axial motion, axial movement along its axis. So apart from it transfers the torque as well as an axial motion. So it is fastened either in the shaft through the set screw, as I said it. And this is a Woodruff key. Woodruff key is an easily adjustable key. It is a piece from a cylindrical disc having segmental cross section. The Woodruff key is capable of tilting in a recess milled out in the shaft by a cutter having the same curvature as the disc from which the key is made, so that it is used to easily fit the hub portion into that one. So this type of key is largely used in the machine tools and the automobile construction. Usually the recess curvature is the same as the curvature, outside curvature of the segmental segmental key. So saddle keys and tangent keys. So these are the flat keys and hollow saddle keys. So flat keys are they are placed on the shaft. One portion, at some portion they have made it flat, so that the flat surface of the key is placed on the flat surface of the shaft. So there is no recess in the shaft. So only recess is provided in the hub region. So hollow saddle key. So at the bottom portion, if you see it, so you will have the curvature, the same curvature will be there in the inside curvature of the key is equal to the outside curvature, that is whatever the curvature radius is given to the shaft is there, so that they can match perfectly. And this works on based on the torque. So here this is having more torque, it is having more torque capacity than this one. So this is because of sliding, it works on only the friction. So hence the limiting, and this is a disadvantage. So the disadvantage of the saddle key is to low power transmitting capacity. Saddle key is liable to slip around the shaft when it is subjected to the heavy torque or even medium torque also. So because of that it will slide. Okay. So the other one is the tangent keys. In the tangent keys, we can have the two square keys are fixed at an angle of 90 degree. Each key is to withstand torsion in one direction only. So these are used in large heavy duty shafts. Saddle keys requires keyway only in the hub portion. Okay. So the saddle keys, actually these saddle keys are in the hub portion, not in the cat and this one tangent keys. So tangent keys has got the same recess in the hub portion, right? So because of this 2 at 90 degree, it can transfer it very large torque in one direction. So round keys are circular in section and fit into the holes, drilled partly in the shaft and partly in the hub. Round keys are usually considered to be the most appropriate for low power drives. If you make this one tapered, so in that case sometimes it can be used for even higher torque range also. So sometimes the keys are made of integral with the shaft, so which fits the keyways broached in the hub. So that means we are providing splines on the shaft. So these splines are 4, 6, 8, it depends. So 10 or 16 splines. So the spline shafts are relatively stronger than the shaft having a single keyway, because there are no keyways. If the keyways are there, then it will be reduced the strength. So as the splines is an integral part of the shaft, so it is more stronger than the keyed one. The spline shafts are used when the forces are to be transmitted in large proportions to the size of the shaft, as in automobile transmission and sliding gear transmissions. So when you want to switch over from one gear to the another gear, so the mating gears are generally they will have an axial moment. It is better than the parallel type key. So this is a key where we are using 4 splines we are used here. Sometimes even 6 or 16 splines are also, it can use it. So for better easy displacement in the axial direction. Okay. So now we will go for design of the key. So the main, as you know that the main function of the key is to transfer the torque, right? So the shaft, it transfers the torque to the key, and then the key will transfer the torque to the hub portion. So there are two things. when it is transferring torque, so that means generally it is you are going to get a shear failure. And the other one, as the key is a different material and it is going to fit in the recess of the shaft or recess in the up portion, as you see here. So that's why you are going to get a contact stresses developed between the shaft and the key, or between the key and the hub. So that means the key failure mainly designed with the design with a shear failure or design with a crushing failure. Okay. So now what is torque? A torque is nothing but tangential force into the distance, that is radial distance. So we can calculate what is torque MT, we can find out by using the power and the RPM with the use of this one, P into 60 upon 2 pi, and if you do it, can calculate what is torque. And if you want to calculate what is the tangential force applied at the tangent at the point of the key, so in that case that can be found Ft, that is if Ft is the tangential load or the F is the tangential force. So F into the distance, so from the center, that is d by 2, if d is the diameter, so then F into d by 2 is nothing but the torque. So you try to remember what is the actually the width of the width of the key is generally it is 1/4 of the diameter of the shaft, and the thickness is equal to 1/6 of the diameter, and the length of the key is equal to 1.5 times the diameter. Okay. So design of key based on shear and crushing failure. So MT is the torque transmitted by the shaft. As I said it, the torque transmitted by shaft is equal to MT, which is equal to the force into the radial distance, that is d by 2. So if L is the length of the key and B is the width of the key, so and T is the thickness, and also if tau s is the allowable shear stress for the key material, and sigma shear is the crushing stress of the material. So in that case, we can write down as the resisting area in shear. Resisting area in shear is equal to B into L, where B is the width and L is the length, which is perpendicular to the slide. So if L is the length, will be there, it will be fail at this point, right? So the area of the section you are going to get is B into L, and it is we can get the torque. Resistance due to the shear is equal to resisting area into stress. So applied torque, that is applied torque MT is equal to the resisting torque, and the resisting torque is nothing but the resisting shearing force into the distance. So what is the resisting shearing force? It is resisting area into the tau s key. So P into L into tau s key into D upon 2, right? So using this I can find out if you know P and L, if you substitute here, you can find what is tau s, that is the shear stress, and that should come less than the allowable stress for the key material. Design of key based on crushing. This is a design of key based on shear. Similarly, we can go for the design of key based on crushing. So when the force is applied in this direction, so this surface, you can see here, this right side surface, it is in contact. So that is here. See here, this from this point to this point, if the applied force is in this direction, so this is in contact. So that thickness is T by 2, right? So it is T by 2. The thickness is T by 2 and L is the length. So what you will get is Mt is equal to, that is the applied torque, is equal to the resisting strength, resisting torque, and the resisting torque is nothing but the resisting sharing strength in crushing into the radius of the shaft. So that is the T by 2 into L. T by 2 into L is the length into sigma CR, that is the crushing strength of the key, into D by 2. So by using this we can find the MT based on the top. Okay. So now the same thing, just I want to explain once again the same thing with the help of board. See, I will take this. I will take the center line. Assume that this is shaft, right? And this is the portion of the hub portion, the mating part. So here, let us take the key of the shaft. Flat key, I will take it. So the force applied torque is here. So if I draw this, if I show it here, rectangle sun key, one side taper is equal to 1:100. Right? So this length is the length of the key, which is 1.5 times the diameter of the shaft, and this is nothing but the width, and this is what the thickness. Now if it is a shear failure, you are going to get the failure along this, so that means you are going to get the failure along the surface, right? So if I draw this dotted line, this is the hedged area of this. So this is the indication of what is the failure in shear. Okay. So if resisting area in shear is equal to the width is B into length is here, right? And what is the resisting stress? Tau S is the resisting stress for the key. So in that case, we can get this that is the applied torque MT is equal to, it is the internal resistance torque. Okay, internal resistance torque, right? Or internal resistance torque is nothing but the internal resisting force into D by 2, right? What is the resisting force? Resisting area multiplied by stress. So normally we are going like this. And what is resisting area? It is nothing but B into L into twice for the key into d by 2. So this is equation 1. From this I can get what is, we can, by substituting P and L, we can get twice that should come less than twice allowable. So this is based on what? Shear, right? So similarly, based on crushing, see here, the force is applied to this point at this point. So I will take, okay. So this area, when I apply the force over here, so we should not take both areas. If the force application in the left side, so this is in contact. So that means here I can show this line, this surface. It is, what will be this thickness? It is T upon 2. So if the force is applied in this direction, so this area is in contact with the shaft, or if you take the top portion, it is in the half portion. So the area in contact is nothing but what is that? T by 2 into L. Okay. If sigma CR is the crushing stress for the key, right? And T by 2 is the height of the key, and L is the length of the key. Okay. Then the applied torque MT is equal to the internal resisting torque. So that is the resisting area multiplied by stress. So what I am saying here is the applied torque MT is equal to resisting area into stress into the radial distance. So that is the diameter P upon 2. The resisting area in crushing, it is nothing but T by 2 into L, right? So that is T by 2 into L into stress is nothing but sigma CR for the key into D upon 2. Yeah, the crushing stress normally it is 1.5 of SYT upon vector of safety. The materials are different, so in that case, I had to find out the crushing stress using this. Okay, so now you can find out. So you just put value of T is equal to D upon 6 here, and L is equal to 1.5 D. Then so you can, this thing is nothing but T by 2 into L into sigma CR K into T by 2. This is the second equation, right? This is based on crushing very well. Okay. So in the examination, sometimes, or in the interview, wherever you go, so they may ask this question that if the crushing stress is twice than the shear stress of the material, is twice the shear stress of the material, then prove that the key used is a square one. For such is a square one. Means we have to prove that. What we have to prove? We have to prove that B is equal to T if sigma CR is equal to twice of shear stress. So in such cases, for this, the solution, the proof for this is, so we know that the torque equation for shear, if you have to say that these things, B is the width of the key, T is the thickness, and L is the length of the key. Okay. So tau S is the allowable shear stress for the key, and sigma shear is the allowable crushing stress of the key. So then the torque based on shear is equal to the area in shear B into L into the tau S for the key, shear stress into D upon 2. This is equation 1. Similarly, the torque based on crushing is T by 2 into L is the area in crushing into sigma CR key into D upon 2. Now equating 1 and 2. Equating 1 and 2. What we can get? Here D by 2 get cancelled out, LL get cancelled out. So what is the remaining here? B into tau S for the key is equal to D by 2 get cancelled out. So here it is T by 2 into L cancel out this and this. So this is sigma CR. Right? So now I will substitute. In this substitute, sigma CR is equal to twice of shear stress. So B into tau S is equal to T by 2 into twice of tau S. So what you will get? 2 get cancelled out. Tau S get cancelled out. What you have proved? B is equal to T. In the same way, they may ask this question that if the key used is a square 1, if the key used is a square 1, so then prove that that crushing stress is equal to twice of shear stress. Again, you have to use the same two equations. Okay, we have to use these two equations. So here you write down these two equations. Tau S into D by 2. This is for based on shear, and based on crushing it is D by 2 into L into sigma CR into D upon 2. This is based on crushing. Now if they give B is equal to T, if B is equal to T, so what happens here? B and T get cancelled out, right? So D by 2 is D by 2 over. So L get cancelled out. So that is tau S is equal to sigma CR upon 2. So R, you can say that crushing stress is equal to twice of shear stress. So we have proved that if it is a square key, the crushing stress is twice of shear stress. The same thing, just I want to convey this one. We are presenting it here. So this thing, it is a design of key based on resisting area is B into L. Okay, B and T is this one. L is the, you can find out MT is equal to B into L into tau S key into D upon 2. Design key based on crushing failure is area of crushing is T by 2 into L, right? And that resisting area into stress into D by 2, you will get what? Torque. It is T by 2 into L into tau S for the key into D by 2. This is based on crushing and this is based on shear. So if the crushing stress is twice the shear stress, the key prove that the key used is a square one. So as I said it, as we had discussed already on the board, the same thing it is given here. Okay, so try to write down the two equations 1 and 2. One is based on shear and the other one is based on crushing, and then you equate both the things for crushing and bearing. Equating that, you can find that P is equal to T. So now one more interesting, that the important thing is the effect of keyways. The effect of keyway, because see, when you insert a keyway in the shaft, so the strength of the shaft will be reduced, right? So if the ratio, that is E, if E is the ratio of the shaft without keyway and with keyway and without keyway, okay, so then we can have that when it depends upon the W and D. So this W is a width of the key, or B is the width of the key. Okay. So these things, that is a scientist, H.F. Moore, he has derived this equation. So by experimentally, okay. So E is equal to 1 minus 0.2 into W upon D, where W is nothing but width of the key, that is D upon 4, and minus 1.1 into H upon D, where H is what? Height, that is nothing but the thickness T. Okay. So here E is the shaft strength factor. It is the ratio of strength of the shaft with keyway to the strength of the shaft, same shaft without keyway. The material, you have to take the same material with keyway and without keyway. Okay. So by taking that, it comes less than 1. You're getting it? So 1 minus of something. So you will get always less than 1, because the strength of this is strength for the shaft with keyway is less than the without keyway. So that's why E should come less than 1. Where H is the depth of the keyway, it is nothing but the thickness, that is T upon 2. H is nothing but the thickness of the key, that is depth of the keyway. So that's why the total height, that is H is the height of the key. If you take it, then you don't get confused with that. So it is the recess what we are talking about this. The effect of keyway, that is, if here, if shaft is here, so this recess, so this is W, and this is nothing but H upon 2, or this is H or T upon 2. If T is the thickness, one half portion it will be there in the hub portion and half portion in the key, so in the shaft, so that's why it is T by 2. Okay. So using that value, we can get what is E, that is the effect of keyway. So if the key length is a long one, so in that case we can find out, that is the twist is increased, that is K theta, that is the reduction factor of the angular twist. K theta is given by 1 minus 0.4, and again here K theta is again less than 1. That is the reduction factor with keyway and without keyway. Okay, 1 minus 0.4 into W upon D minus 0.7 into H upon D. So these are the equations he has formed with experimentally. Okay, so this thing is very important for learning. So sometimes they may ask in the examination or in the interview, wherever you go there. So they will ask what is the effect of keyway. So it will reduce the strength of the material, or strength of the shaft. So by how much it will reduce, so that is given by these equations. Okay. So in the conclusion, so keeping in view to enhance the life of the machine component, discussions are made on the functions and types of keys. We discuss various keys, and we have designed the sunk key, taper key. That is, one is for the square and the other one is rectangle sunk key we have designed. And the effect of keyway also we learned. Thank you.